Thank you, Enrico. Thank you, guys, for the invitation. It's a very nice series of seminars, and I'm very happy to see that it grows and it goes very well. So, I'm going to give a talk more or less like a class or a course, I thought, because this is something that we have done recently, and we want to kind of emphasize a little bit the technical details. So it will be a little bit technical with some notation that I would like to explain. Hopefully at the end I would be able to ask a few interesting conceptual questions that arise from this observation. So this talk and this work combines two things that, they seem very different. It's thermal field theory and on the other hand, and then conformal ladder integrals on the other hand. So let's start with some context, which is actually historically how this work has started. We wanted to study, as many of you, and an increasing number of people as well, want to study thermal two-point functions in conformal field theories. So the simplest thing to do is to have scalar fields in a space-time which is the thermal space-time S1 cross RD1. One of the scalar fields is located at the origin, the other is in some distance r. So I'm just explaining here things that everybody here probably knows, and imposing in the simplest case periodic boundary conditions on the fields. The relevant quantities, the relevant variables are explained in this diagram. Okay, so in general, as again many of you know, when the distance is less than b, the inverse temperature, then if the theory is a CFT, there is a general expansion of the correlator, which is given here. And what one notices is the presence of these Gegenbauer polynomials with the powers r over beta, and usually they are called the thermal conformal blocks. And of course these coefficients here, the AQs here, and of course the spectrum of the operators. Now, the first thing I would like to emphasize is that this is a thermal field theory. So these coefficients here, in principle, they should be thermal averages of some operators. So there should be, in principle, a way to write them in the usual way as thermal averages. If you have a Hamiltonian, we will have to take the trace and divide by the partition function. Okay, that's a general remark. And now, there are explicit calculations that have been done along this direction. For example, for massless free fields, the result is known. It's a sum over images. For example, you can do it in many ways. It has been done in the 80s, even before, when people were looking in thermal field theories. So these coefficients here are proportional to zeta functions, and in particular for massless free fields, sometimes people call them generalized free fields because they want to work in general dimensions without any coupling to gravity, for example. But anyway, so for massless free fields, in the simple case of a unique scalar, these guys are proportional zeta functions with arguments d minus 2 plus s. S is an even number, and the interpretation is that the operators that they correspond to these things are conserved higher spin currents. That's okay. But of course, one would like to answer the question more generally. And there are, as you know again very well, there are many efforts to answer this question through the thermal conformal bootstrap. But if you want a more traditional way of answering this question, is to just go and evolve the two-point function by any way that one knows, for example, RG, deformations, nonlinear equations, etc., and see how this evolution will be mapped into the CFT expansion. Okay, so suppose that we evolve it and we go into a new CFT, which involves some coupling constants here. So what we expect in general? We expect that, for example, the dimension of the field phi will change as a function of the couplings. We expect that the spectrum will also change. We expect that these thermal one-point functions will change, and also the dimension of the fields will change. But in general, the Gegenbauer polynomials, we expect them to be the same, each one corresponding to the contribution of a certain field. Now, it is a belief in a CFT, I'm not sure if it is completely proven, but it's a belief that in general there should be an OP expansion that involves a unitary reducible representation of the conformal group. So in this sense, the spin should be an integer number. So there is it shouldn't depend on the coupling constants. But of course, the scaling dimensions can change. Right. So now let me notice the following thing. In the free result, if you allow me to just review the free result, which is here. Okay. In the free result, the dimension of these higher spin currents was exactly d minus 2 plus s, as you know, and if you substitute that there, along with the dimension of the elementary field delta phi, you find that the contribution of the Gegenbauer polynomials of these higher spin fields is of this form, Rs, Gegenbauer polynomial S, and this is actually, these are terms that are annihilated by the d-dimensional Laplacian acting on X. So that essentially means that the two-point function, the thermal two-point function, the free field, is actually a Green's function for this Laplacian, because all these terms will be annihilated. But there will be one term with a delta function which will come from the leading singularity, as we all know. So, well, I say that because we will see an interesting effect in the following. And that what started, that's one thing that started this investigation. Okay. Now, let's see how we can deform the theory. And of course, you can choose your favorite deformation of the free theory. And we have chosen in a number of works to deform the theory in the simplest possible way, which I will call the integrable deformation, because actually we can do the calculation. Integral deformation involves a Gaussian deformation. Perhaps I should put here Gaussian deformation, which is the following. I consider now a set of complex scalars which have a mass, a common mass, and interact with an external gauge potential A mu, which is very simple like that. It has only the zero or the temporal component. And this, you can find this model in many interesting other models. It can be an interaction with an external magnetic field. It can actually come in CPN models, etc., etc. Now, okay, as I said, this model is integrable. You can actually calculate it in many ways. One thing that you can notice is you can do a Hamiltonian analysis. You can find the usual Hamiltonian, which I will write it in this form. So it's a free Hamiltonian H0, which is deformed by a mass, and a so-called imaginary chemical potential. You can think about it in this way. In any ways, always the A0 component of the gauge field is usually a chemical potential, real or imaginary, depending on your signature. Usually, again, I remind you that in many cases, we drop this A0 component fixing the gauge, but it's not necessary. Now, okay, so the deformation, this theory is like a deformation of the original theory, deformation of the original Hamiltonian by a mass term and an imaginary chemical potential with the corresponding operators, phi square, and the U1 current operator, which I wrote here. D here is the covariant derivative in the temporal direction. The reason why I wrote down the Hamiltonian is because eventually I would like to calculate thermal correlators, and then it's very nice to have a Hamiltonian to make contact with what we would expect. Okay, so the calculation can be done. It's not that hard. Now many people can do this calculation. In fact, the two-point function is easy to calculate. What is more difficult, but still doable, is to expand it in this Gegenbauer polynomial basis, or in the thermal blocks, conformal blocks basis, and but it can be done. And the spectrum is the following. Let me talk to you about the spectrum. Now, the spectrum involves higher spin fields with dimensions d minus 2 plus s plus 2t, where t is the twist now. So it involves operators that have more boxes on phi. Before we had only the higher spin conserved currents, d minus 2 plus s. Now, also s can be even or odd. So we can have spin 1, spin 3 operators here. But also it involves another set of operators that did not exist in the free field theory, so-called shadow operators, which are scalars, only scalars, with dimension 2k, where k is 1, 2, etc. It starts with dimension 2, which is the usual shadow scalar sigma, the shadow field of the phi square operator. It has been discussed in many times. This comes about if you do a Haber-Sardonovich transformation. Okay, you can find this shadow operator. So this is how the spectrum changes. And now notice also that I have used this variable, which will play a central role, this z variable, which is like a modular variable, because everything is written very nicely in this new variable. So let's see what happened here. we see that the spectrum has changed, but the interesting thing is that the anomalous dimensions, or the scaling dimensions actually, they still are canonical, so they are not anomalous. All these dimensions have remained canonical, so there are no anomalous dimensions. This is what I should say. Also, the shadow fields here, they have again canonical in a sense dimensions, because nothing depends. The dimensions do not depend on the deformation parameters. The only thing that depends on the deformation parameters are these coefficients here. Now, notice that the 2-point function now is no longer a Green's function of the Laplacian, due to the presence of higher twist and shadows. So this is an interesting observation, and probably has some deeper meaning, which we need to understand. Now, the second observation, which it should come as a surprise, is that, well, this is not a conformal field theory. This is a massive theory. So why should this have an OPE expansion as a would-be conformal field theory? So the expansion is CFT-like, despite being massive. So for every value of the mass, I can write this expansion. So, and I emphasize it is not a CFT. It is like I use the basis of conformal blocks. Indeed, also the shadows, they do not have Gegenbauers because they are scalar terms. They're just, one here. But I use this basis and I deform the coefficients in such a way that I get my new thermal correlator, but which is not conformal. So I haven't imposed anything here. I just did the calculation. So that is a kind of surprise, which led us to investigate a little bit further. Now, I write the formula now for the coefficients here. And it is a complicated formula. And since this is complicated, we simplify it by choosing the dimensions of space-time to be odd. And because it is odd, I write it like as 2L plus 1. And the reason we chose it is because in that case, this sum here is finite. It's the sum of polylogs, and it is finite. If we had chosen the even, we can still do the calculation, but it's an infinite sum. And of course, it's more complicated, but of course, it's also interesting. Okay. Of course, so you can interrupt me anytime as you want. Let me understand the question. Yeah, so I must say that we have not discussed the radius of convergence of this expansion. But why you think that this is modified? Because here, sorry. Yeah, yeah, I think I agree with you. It could be modified, and studying, yeah, the convergence properties, or actually the analytic properties of this expansion. Now it's an interesting thing, but yeah, we haven't studied that. This is we were drawn into more mathematical stuff, unfortunately, at the moment. And I think it's a very interesting question. But yeah, we were drawn by somehow the beauty of these results, which I'll try to explain now. So yeah, okay, this is a result. It looks complicated, of course, to somebody that sees for the first time. I just emphasize this fact that here you can see that it has an alternating sign depending on the spin of the corresponding operator. So for even spin, this thing is a minus. And for odd spin, this thing is a plus. For odd spin is a minus, I'm sorry. For even spin, this is a plus, I'm sorry. And this is very important, which actually complicated the things. For even spin, it's a plus. For odd spin is a minus. And this is very deep, as I think we understood after a year or so by playing with that. Anyway, that's the result. Now, to complete the context, because we now want to interpret this as a thermal two-point function, we can also calculate the free energy, which is actually the partition function, and then the logarithm, which is the free energy. The calculation can be done, again, using field theoretic methods. So that's the logarithm of the partition function, and now I start putting L here to denote the dimension of space-time instead of D. And so that's the result. Here is the real part of the corresponding polylogs, and the sum again is finite. Okay, since I have the free energy, this means that I can calculate thermal one-point functions taking appropriate derivatives of the above. So, well, just before I wrote the Hamiltonian. So the partition function is the trace of the Hamiltonian, and the Hamiltonian is deformed from the free Hamiltonian by the mass term and the chemical potential. So taking the derivatives with respect to the mass term and the chemical potential, I could calculate the thermal one-point functions of phi square and also of the U1 current, and they would correspond to these two coefficients. And I can assure you that indeed this is the case. Taking derivatives of these coefficients, I reproduce these first two guys. Then you have to ask me, what about the higher spin currents? And I will come to that in a moment, after I introduce now some notation. And this is where somehow one needs to get into more technical stuff, unfortunately, because the thing becomes, I think, a little bit complicated, and so we need to clear up what we are doing. Okay. Now, as I said, we have calculated the thermal free energies of free fields, free massive fields with a chemical potential, and we were not the first ones, obviously, this is clear. But these things have an apparently overlooked property, which perhaps it was noticed, but anyway, we noticed it as well. And I haven't found it very easily in the literature. Let's start now with something which is very simple, which we call the parent quantum mechanical model, which is just quantum mechanics of two harmonic oscillators, which I wrote here, P1, P2, and these are the two harmonic oscillators with the same frequency, which I now conveniently denoted with M, but also interacting through an imaginary chemical potential. And for those who are careful enough, this guy is nothing but the J3 guy of the SU2. His system is very interesting. It has many interesting properties, an SU2 symmetry. This is a kind of angular momentum, but in the third direction, not in the plane where the fields live. But again, this is a system whose Hamiltonian is free part, a massive deformation of this operator O, and a chemical potential imaginary of this other operator, which is a charge. Now, one can play with that. It's a simple exercises for your students, and using an appropriate set of creation and annihilation operations. You have to combine the usual annihilation and creation operators to find this. Okay, you can write the Hamiltonian plus the mass square term as a sum of these number operators, and you can write down the charge as the difference. Essentially, again, for some of you, this should remind you of the Schwinger model, which is two harmonic operators whose spectrum generates the SU2 irreducible representations. But I'm not going to dwell on that. Now, then we can calculate the thermal partition function easily. I just repeated a few calculations here. These are simple exercises, and I write down the partition function in this way, using the same z variable that I had before. This is, again, an interesting way to write the partition function. It is not very common because everybody, uses the exponentials, etc. But the z is telling and tells you something. All right. Now, in this Hamiltonian quantum mechanical system, we can actually play and we can define things easily. So, if I wanted to define the expectation value of the one O operator, which is this guy here, then I would take the derivative with respect to mass square. So let me define this operator. And written in terms of the z variables, again, it has a very interesting form. If I wanted to define the expectation value of the Q operator, then this is the form of this operator. So these are two operators that it would be nice to have in mind. And again, indeed, yes, if I want to define this expectation value, I take the derivative of the logarithm and I find something. Again, the expectation value of the Q operator, I take the derivative and I find something else. Now it's an interesting observation, again trivial but interesting observation for the future, that these guys here are harmonic functions, one of them, the O in the open disk, the other one in the upper half plane, taking constant values at the boundary. So these may be words, but for some of you they may ring a bell in what people talk recently, ADS2 CFT1 correspondence. So essentially, these are like bulk-to-bulk boundary propagators in the ADS2 CFT1 correspondence, and that should be relevant for what we discuss later. Right, this was quantum mechanics. Why did I say that? Because from this quantum mechanical partition function and free energy, I can calculate the free energy of the massive free fields. Again, as I said, this is probably known. I cannot imagine that nobody has done it, but somebody should have done it, but it's not easy to find it. And it's also very simple. Use the free energy as a single particle free energy and use a one particle density of states for a relativistic particle, which is this thing here. It's very easy. It's like the calculation of the number of photons in the Planck calculation, if you assume a relativistic dispersion relation. So using that, you integrate log z0, okay, and I can assure you, that's the result. I leave it as an integral, I leave it in this form as an integral, and here I just explain this is the relativistic dispersion relation, but there are a few things that I need to explain. I assume that my system lives in d minus 1 dimension, so I have a spatial volume which is like that. So I have to assume a length scale L. I quantize my spatial momentums like that, like in a box. And then that means that I have to introduce a parameter like that, like alpha square, L square over 4 pi beta square, which is a dimensionless parameter that is there to some power to tell me in how many dimensions I am, how many dimensions I've done the calculation. And the result is, if I do this simple integral, well, it's maybe not so simple, but it's also not complicated. This integral is exactly the partition function, the free energy of the free fields, massive free fields that I have done. And then I'm using Z and Z bar again, the same as before. And of course, okay, this is the overall scaling. Remember, the left-hand side is a calculation of a free ideal gas, which I put in a volume. The right-hand side is a path integral calculation. Again, I need to say something about the infinite volume. And the difference is this alpha parameter here. Now, again, bear with me to introduce a little bit more notation. The thing is that the partition function and the free energy of my model, the free massive complex scalar fields, comes from the partition function of the free energy of this model of the harmonic oscillators. Okay. That was an observation. We went a little bit further, and the integral that gave this partition, this free energy, can be written in a very suggestive form that actually has been used from people in other research directions, and in particular in calculations of multiloop graphs. And this is now going towards the connection that I want to make. So the same integral that I wrote before can be written as iterated integrals. There is a full mathematical story about iterated integrals. Okay, so this is a product of integrals. So I integrate and I integrate again, I integrate again. These are iterated integrals, but I integrate in some order. So it's an ordered product of iterated integrals, and the order of integration is shown here from the lowest indices to the highest indices. The highest index is L here. Okay, so that allows us to define now an integral operator. This is the single integral operator, with which I act on my log z0 many times this way. And so this is a definition. So this is my integral operator acting L times on the free energy of the harmonic oscillator, and gives me exactly the free energy of the field theory. Okay. Now, having this at hand, it's very nice now to, instead of thinking of the field theory, which is a complicated thing, to think about the quantum mechanical model. Everything I can do in the field theory, I can first do it in the quantum mechanical model and then translate it into the field theory. So another interesting set of functions, thermal expectation values, actually, all these are thermal expectation values because I act on the logarithm of the partition function, which is the free energy, but of the quantum mechanical model. thermal expectation values of a quantum mechanical model. So if I acted one time with this LZ, I would get the expectation value of this Q operator, which was the charge. But I can act actually more times. So I can, calculate in a sense something like Q square. Well, it's not really Q square, but I can act powers of this guy. Now, why I will do that, I think it will become obvious later, but let me give you the result. If I act with this operator on the free energy of the harmonic oscillator, I get something like that. It starts looking familiar. And I denote it as D calligraphic 0, 0, this is 0, and K, because I acted K times, and I call this a depth. Okay, now why this looks familiar? Because this 1 over 1 minus Z to some power looks like a massless propagator. Looks like a massless propagator for a field. Okay, it may not look obvious to you now, but I think it will become obvious later. Now, this parameter K is the depth, and actually acting with this operator this operator LK here, which is not, it's a little bit more complicated, it involves this K. Acting with this operator LZK, it raises K by 1. Okay, this is notation, and that's why I want to summarize it. I think it is important. Just to get an idea. So what did I do? I calculated the partition, the free energy of the harmonic oscillator. I denote this as D00, and this is the result, simple result. The free energy of the D-dimensional field theory, now I denote it as DL0, 0 depth, and this guy here, I denote it K depth and 0 L, which means 1 dimension, and this comes like that. So I have defined 3 operators, D, L, differential operators, and this other D small, which is an integral operator. They all commute with each other. You can prove that. And now, with this operator, we build things as following. The free energy of the D-dimensional theory is built by acting with this operator L times on the free energy of the quantum mechanical model. If I act with a D, big D operator on the free energy in a dimension D, I get the free energy in a dimension D minus 2. So this is D dimensions, this is D minus 2. But this guy is the thermal 1-point function of my operator, which is actually phi squared, this operator, in dimensions D. So I learn that the thermal 1-point function in dimensions D is equal to the free energy in D minus 2. If I act with LZ on the logarithm of log Z, I get the expectation value of my other operator, my spin operator. And also, if I act with the integral operator on log Z, I raise the dimension again by 2 with a minus sign. Okay. Now, we wanted to have this notation because all we have done now, it will be translated, or perhaps better, mapped into a completely different story, which is the story of conformal ladder integrals. Let me again briefly go into this story, more briefly than I did until now. What are these integrals? These are integrals of the form that I show here. They are conformal. I think I have also a graph just below to show you what are these integrals. They are conformal in the sense that each of these integrals can be written in this form. You can take out this factor, and the rest is a function of the two conformal ratios. Using conformal invariance, if you multiply by x to 4 to the power 2l, and you take the limit, which it will be shown later, you take a particular limit, you fix 3 of the 4 points and you keep just one to this Greek zeta. This is Greek zeta, and you will see why. This becomes a function of zeta and zeta bar, which can be again written in this form, a function of zeta and zeta bar. So what are these integrals pictorially? These are the L-loop integrals of this form, x1, x2, x3, 4. At each point, you may have a coupling like g square, which essentially is a loop counting parameter. It has to be a marginal coupling. And then if I multiply this by x to 4 to the power 12 and I take this limit here, the integrals become like 3-point functions, z, 1, and 0 here with L lines. And the propagators here, and here is now the interesting thing, the solid lines are like that, 2k. Now, I emphasize the notation because I used exactly the same letters to which in the two different cases mean different things, but then we will match it. So I used, I'm sorry to just go back, I used d equals 2k plus 2 dimensions. K is the same k that I denoted depth before. And L loop is the same L that I denoted above, and as you will see below. So my integral is in even dimensions. And these are the integrals that appear in calculations, in particular in 2 and 4 dimensions. These are the integrals that people have calculated. So it's the same k, and it's, in this language it's the different k and different L, but then we will match them exactly. So yes, indeed, this k here comes here, and the dashed line is a propagator of a field with dimension 1. And that makes the graph conformal. Right. Now, a remarkable result by Isaev some years ago, using conformal quantum mechanics. This is a big mystery to us, and to everybody, how our results are related to conformal quantum mechanics, yields the value of these integrals in the variables zeta and zeta bar. Remember, the zeta and zeta bar are the conformal ratios. The result is just a single integral, again with k and L given exactly by the loops, and k is the power of the propagator. We do a change of variables. This is our contribution. And we bring the result for phi. Phi, I recall, is this guy here. I extracted the factor of 1 minus zeta to the 2k. So that's the difference between this guy and this guy. So again, for phi, the result is like that. Here is the function that I denoted as d calligraphic 0k, and that's the integral. All right, so here is now the correspondence of these two calculations. They look very different. They discuss completely different physical quantities in a sense, but they are exactly the same. If we do the following, if zeta is associated with z, remember zeta is a cross ratio, z is a kind of modular parameter, and if this coupling g is associated to alpha, this parameter, they are completely mapped. So on one hand, I have this integral, which is given by that. On the other hand, I have what? I have something that I get from log z0 acting k times with this operator and L times with the integral operator. Okay, I divide by this thing here. So this k times and L times acting on the partition, on the free energy of the quantum mechanical model is my definition of this thing, which is called calligraphic dLk, right? So they are exactly the same. And another inviting form of this correspondence is that the conformal integrals are like a ratio of these two d functions, and the difference, remarkably, as I will try to argue, is this factorial factor here. Okay, so what did I do schematically, and why I think it's an interesting thing, is that now using L and D, we can start from the partition, the free energy of the harmonic oscillator, act many times in any direction we want with L and D, and actually they commute with each other, so I can act in any way I want, and I produce these functions D, L, and K. And these functions D, L, and K, as we just said, they are exactly related to the conformal integrals. So we have a way to produce L-loop conformal integrals in K dimensions, in any dimension we want. For the interesting thing is that the integrals in 2 dimensions, which means K equals 0, like these guys here, K equals 0. So these are the integrals in 2 dimensions. These are the integrals in 4 dimensions, etc. The integrals in 2 dimensions are integrals which involve lie plus lie. I made a case before for that. I made a noise. But the integrals in even dimensions, they are lie minus lie. And what everybody was doing the integrals in 4 dimensions, so the only integrals that were known in the literature until recently were the 4-dimensional integrals. We communicated with some people and we agreed eventually, we did the calculation, that the integrals in 2 dimensions, which are a little bit singular, they give lie plus lie. And then recently there was a paper by the Isaev group, etc., for integrals in 6 dimensions, which involve the combination of the 2, and we agree on the result. So we have the results, but they have not been calculated in another way until recently. I think also they did it in 8 dimensions in this recent paper. So it's a very nice construction. But there is more to that. Again, these are the functions that we can build from the harmonic oscillator, and they correspond to thermal one-point functions. They satisfy a remarkable differential equation. I say remarkable because if I write it in the variables m and mu, it looks like that. Well, it's an equation that is like a Laplacian, but it has 2 eigenvalues, this L and this K, that appears like K minus 1. So this is like rotation. Now, this is it's an equation that is very intriguing, but it's puzzling, still not understood. We are talking with people who are doing modular environments. It's like a modular equation. Essentially, I'm telling you that the thermal one-point functions satisfy some modular equation. One way to understand this is for L equals 0. That means in D equal 1 in quantum mechanics, this equation coincides with the equation of motion of a scalar field in Euclidean ADS2 with this metric. This is the ADS2 metric. And mass, which is like that. This is like the Kaluza-Klein mass. So these guys are bulk to boundary propagators. I said that before. Boundary propagators in the case of ADS2 CFT1. For operators at the boundary of ADS2 with scaling dimension k. So the thermal one-point functions are like bulk to boundary propagators. So I recap what I have suggested so far is that from the thermal one-point function point of view, I have a theory that lives in d dimensions. I consider thermal averages of depth k. K0 is actually, zero depth, K1, 1 depth, etc. I have a mass and chemical potential, which are my deformation parameters, and I have a geometric parameter, is alpha square. And this corresponds exactly to the dimension of the integral, the loop order, the space-time points now correspond to the mass and the chemical potential. Actually, these are the crossing ratio, and the coupling corresponds to alpha. So, back to the thermal two-point functions and to the question. We've managed to evaluate only the spin 0 and spin 1 thermal one-point functions. That was my beginning step in the beginning. So this guy and this guy. So what about the higher spins? Well, this theory is massive, and so we do not have higher spin conformal currents. But the thermal expansion requires the presence of higher spin conformal currents, otherwise we cannot write this expression. I think I mentioned that before. So what are these guys here that we have found and calculated? Well, okay, what saves the day is that we are in a free theory and we can construct explicitly the symmetric traces and conserved conformal higher spin currents that give rise to these functions. This is again a little bit technical. I will not bother I will not bother you with that a lot. I can construct an operator which is a symmetric conserved traces higher spin explicitly. I subtract the traces here. This is the Hermitian conjugate. And this guy will get an expectation value. And it's the usual expectation value. And this B one-point function is related to this A by a usual thing. We had to work this out. Now, a tedious calculation gives a recursive relation. The thermal one-point function of a field with spin s plus 2 in d dimensions is related to the thermal one-point function of a field with spin s, but in d plus 2 dimensions, plus another one with spin s in d dimensions. So that means if I want to calculate the energy momentum tensor, I will put s equals 0 here. And so this guy will be 2, and so this will be 0, and this will be 0. So the energy momentum tensor one-point function will be a sum of the one-point function of scalar fields, but one of them will be in 2 dimensions higher. So the explicit expression in terms of these coefficients, which I gave you before, is this. This is a kind of remarkable expression between polylogs. It's not so easy to verify that because I have given you an expression for this, a general expression. Now you have to show that this, is satisfied, and it is satisfied. The derivation is possible because I had a free equation of motion of this form. So the higher spin operators are determined by lower spin operators in higher dimensions. So eventually the thermal one-point function of higher spin operators is given as a sum of scalar or spin 1 thermal one-point functions in higher dimensions. So the spectrum in a given dimension of higher spins looks to be related to the spectrum of lower spins, but in higher dimensions. There is a kind of duality between dimensionality and spin. Okay, so that's the picture. if I am in dimension, if I am L1 means 3 dimensions, spin 0, the spin 2 guy here will be given by the spin 0 guy in the same dimension plus the spin 0 guy in 5 dimensions, etc. For the other spin guys here, they will be given by lower spin guys. All right. Now a final thing, if I have 3 more minutes, is to tell you about what we call the hyperpartition function. Because we have the partition function and the free energy for any dimension, we thought of summing them, or actually for the partition functions, multiplying them. For the free energy, it's the sum. What is the meaning of that? It's like a partition function of fields in infinite dimensions. But remember that L in the other language corresponds to loops. So that makes sense. We add loops in the other picture. Right. This guy, the full log z actually satisfies a single first derivative equation in terms of the variable m. It can be integrated. Okay, I'll just give you the result. Let me go here. And here is now where the famous 1 over L factorial appears. Right. If I just do the summation, which is like summing the graphs or summing the partition, the free energies, I can get a result. If you look, this is an integral. Actually, there are some divergences, but this integral is very badly divergent as well, irrespective of these divergences that appear here. This is like an error function. It's a positive, okay. But if I wanted to sum, instead of the partition functions and the free energies, if I wanted to sum the graphs, the integrals, the summation involves minus g square. For reasons, if you do the calculations, you will find it. And because the ladder integrals are related to the partition functions with this 1 over L factorial, what I need to do is to add the logarithm of the partition functions with 1 over L factorial, which is the Borel summation. And this can be done with this 1 over L factorial, can be done, and it leads to a very nice result. And this I here is a Bessel function. So we can do the integral, we can do the summation, and it involves a Bessel function instead of an exponential. Now, okay, as I said, the usual, we needed to sum the integrals with minus g square. That means that we just make a rotation alpha to ig, so that we have alpha square is minus g square. So I need the Borel summation of the analytically continued result. So instead of having a modified Bessel I have the usual Bessel of the first kind j, and that's the result. And now you can actually look at that and you can see that the divergence comes from the vacuum energy only of the quantum mechanical model, and everything else is finite. And eventually, this was the result for the summation of the graphs in 2 dimensions, because log z is the graph in 2 dimensions. To get the graphs in 4 dimensions, I need to apply LZ to go to depth 1, go to depth 1. So it's very easy. I just apply LZ here. It's not difficult, and I get the result. And this is a famous result that was obtained by Broadhurst and Daviditsev many years ago, and it is used recently in many calculations of n equal 4 super Young-Mills, etc., etc. You can see that this can be generalized. So, right, it's 1 hour and 2 minutes. So can I have 3 minutes for my outlook? Okay. Sorry, I went a little bit fast at the end. It was a little bit technical, but I thought that it is, if one wants to dwell into this business, I think it has to be clear what is it in one hand and what is it in the other hand. Okay. So I think we are quite excited for this avenue. I think it's an avenue because it opened many possibilities. I think it's a kind of correspondence, but this word correspondence is heavily used, and okay, let's avoid it. So the first thing one notices is that this is like an AGT-like result. For those of you who don't know what is AGT, I'll die. Tajikawa and Gaiotto is the relationship between correlation functions, 4-point correlation functions in 2 dimensions and partition functions or free energies in 4 dimensions. So the conformal cross ratio of the 2-dimensional conformal blocks, actually, which are used to build 4-point functions, the conformal cross ratios Z and Z bar are related to moduli of instantons in 4 dimensions. I strongly think that this is, very similar to what we are doing, but we don't have supersymmetry or any other, mathematical language to confirm that, but this is what happens here. Now, I try to emphasize that it was important to do the Borel sum. It was important that the graphs corresponds to 1 over L factorial the thermal 1-point functions. So summing of the graphs means Borel sum of the thermal 1-point functions. That is of the free energies. The thermal points are free energies. So it is reminiscent of a genus expansion. Now, well, we can consider other deformations, not only massive deformations, but deformations like phi to the 4th, where the equation of motion is different. And it would be nice to see how this goes into our language. Then, does the KMS condition of thermal 2-point functions affect the thermal 1-point functions? We have a calculation in the simple quantum mechanical model that I talked about, that if I insist that my 2-point function is KMS invariant, which is trivial, then I can find the thermal 2-point function, the thermal 1-point function of my operator. Let me just write it because it's something that we discussed. So this is the quantum mechanical 2-point function. If this is KMS invariant, I can tell you what is x squared, the thermal 1-point function. It's a trivial calculation in quantum mechanics, but this is the aim of of many people. From a KMS condition, calculate the coefficient. This x squared is a coefficient. It doesn't depend on t. It's one of the coefficients in the expansion. We can talk about that at some point. But okay, that's a very trivial thing to do. Now, the second order differential equation obeyed by these functions here is closely related to differential equation obeyed by modular forms, as I mentioned. So I think this connects thermal 1-point functions to string amplitudes, because these equations are the ones that satisfied by string amplitudes, and actually they are called, mass differential equations. So it's an interesting thing if these coefficients are related to string amplitudes. That's one, thing. Now, it can be also studied, it can be used, our formulas can be used in various integrability studies. I'm not very big expert on that, but recently our operators have been used to show a total-like structure of ladder integrals, and also to prove the so-called antipodal symmetry of conformal ladder graphs. It was amusing to notice that, and it was appreciated, actually. Well, what about conformal? The final thing is, what about the conformal invariance of the thermal theory? I told you this is not a conformal theory, despite the fact that I used all the conformal thermal blocks, and it is also related to conformal integrals, but it is not a conformal theory. To be a conformal theory, the coefficients, these coefficients, have to be numbers. So how can we find these numbers? Okay, that's also an old story. For example, you can notice that the coefficient of the phi square guy, because its dimension did not change, because the dimension of phi is this and the dimension of phi square is d minus 2, this guy is t independent in the expansion. Everything else is t dependent. This guy stands out, it's t independent. Now, what do you do with this guy? It's like, I think it is like a boundary condition. Do you want this guy to be there in your conformal field theory? I don't have an argument why it shouldn't be there. Actually, in the free field theory, it is there, and it is, as you know, it's proportional to zd minus 2. But in vector models, this operator, phi squared, drops out from the spectrum at the non-critical and non-trivial critical point. So actually, what you would like is to set it to 0. And this gives algebraic equations for beta m, if I assume that the chemical rotation is 0. For example, these are the two equations in d equal 3 and d equal 5. In the first case, the result is a real value for bm, and you get something, the usual, the known golden mean. In the d equal 5 case, the result is complex. So what do you learn from that? You learn that in d equal 3, the non-trivial CFT is stable. For d equal 5, the non-trivial CFT is unstable. And you can actually play this game in higher dimensions. So there is also, more life into this business, because it is not, again, very clear to us how to use this in order to really find the spectrum at the non-trivial fixed point, other than these observations that we have made. So it will be very interesting to continue in this direction. So thank you very much for being patient with me.